Yeah, good morning students. So please type in the chat box, am I audible? Yeah, please type in the chat box, is the audio and video fine? Good morning guys, so please confirm the audio and video, it's fine, right? Yeah, right. Okay, so let us start today's lecture, basically lecture number 13 of this fast track. And in this lecture, we'll basically look at this dimensional analysis and also certain dimensionless numbers. And also I'll give you some introduction to compressible flows actually, okay? And in tomorrow's lecture, like before going to today's class, I would like to explain you certain schedule that we will generally follow. Like in today's session, we'll try to talk about dimensional analysis, and also compressible flows a bit, okay? So this also we'll try to talk about compressible flows. And as you know, tomorrow there is an extra class, like timing is from 11 a.m. to 1 p.m. I'm gonna leave you before the World Cup match begins, okay? So 11 a.m. to 1 p.m. tomorrow, that's like 19th, I guess. Tomorrow is 19th, right? Yeah, Sunday basically. 19th 11/23. So here we'll talk generally about a bit of introduction to turbulent flows, and also we'll talk about hydraulic machines. Okay, so this is how we generally follow. The only thing which I was not able to cover because of time constraint is potential flows. But for potential flows, I have told you that this complete detailed course lectures of potential flow, there are total 4 lectures. If you focus, it will take you roughly 8 hours to finish, okay? So complete potential flows in terms of complex numbers, it's uploaded in the English channel, okay? So you can go there. So this is the way roughly that I'm going to follow, because I was not able to cover potential flows because of certain time issues, but that potential flows will post it in the, we have already posted it in the English channel, okay? So please go further. Is that clear? Fine to all of you? Because I felt potential flows is exclusively for XE, but in mechanical you have compressible flows, so I thought of finishing it here, okay? Right? So let us see in last lecture what we have talked. We have talked about boundary layers. And we have seen certain things like displacement thickness, theta, energy thickness, and most importantly we have seen scaling analysis, correct? Scaling analysis. So in scaling analysis we found out the pressure gradient in the cos streamline coordinate is always 0, okay? And for flat plate, or generally if you write the equations, boundary layer equations are something like, continuity remains the same, so dou u by dou x plus dou v by dou. Of course we have seen 2-dimensional boundary layers. And also the momentum equation stands like u into dou u by dou x plus v into dou u by dou y is equal to u infinity du infinity by dx actually plus nu times of dou square u by dou y square. So this is the equation which we have left with. So these equations are the important things, and if you see, this equation is by default incorporated in this. So that's why when we write momentum equation, we will generally write only in the x momentum equation, because this term manipulation in the x direction equation already gives you the information about the y momentum equation, which is dou p by dou y is equal to 0. And we have seen how we have replaced this term. This term is replaced from this free stream product dp infinity by dx, means pressure in the fast stream is equal to u infinity du infinity by dx. This is what we have seen, right? So these are the things that we have seen here, and yeah, clearly we have this particular equation. So these are the things that we have seen. So in today's session, I thought of starting dimensional analysis, but before this, I just want to talk about one topic, because I'm not dealing potential flows right now. We'll talk about drag and lift forces here itself, okay? Because potential flows I'm not taking right now in this particular course actually, because in the uploadings you can have detailed analysis about drag and lift, but again some 5 to 10 minutes we'll have a quick discussion. Okay, now if you see drag and lift here, drag, resistance in the movement of a body that's offered by a fluid, actually. Now if you see drag, normally drag is due to of two forms in general. One is called the pressure drag, and this largely depends upon shape of the body, so that's why it's also called form drag sometimes. Okay, like for example, let us suppose if you're going on a bike very fast, okay, then definitely you'll experience certain resistance, the pressure of the air pushing you back, correct? You might have seen this. Normally if you drive your bike at very high speed, then definitely the air which is actually stagnant if the air is stagnant, you are moving at high velocity. So at this situation, what happens? You'll feel a lot of pressure is actually pushing you. All your clothes and all will try to swing in the backward direction because there is a high pressure which you are creating, and this pressure will actually try to restrict your motion. So which is called the pressure drag. And second, obviously the viscous drag. Viscous drag. It's also called friction drag. So as you know, every fluid has got certain viscosity, so that opposes. Okay, with this we are studying from long back, and also pressure drag actually. Now, good morning, Prit. So see here, in these two cases, definitely what we do is we'll try to do certain analysis, and finally we'll achieve something called coefficient of drag in this case. Okay, so CD of pressure and CD viscous. This CD is actually called coefficient of drag, and this depends on a lot of things actually, okay, which I'll show you maybe in dimensional analysis also. Coefficient of drag actually. Okay, so this is coefficient of drag. Now for any body moving in fluid, the effect of these two combined is taken as CD pressure plus CD of viscous, and this CD is what we'll use in calculating the friction or the drag forces acting on any particular body. So in general, if you have a body, for example, if you have a body like this, and let's say the fluid is actually flowing at some angle, maybe like this, if the fluid is flowing at UG infinity, and this is a body having some density, having this is a body actually, then definitely when this fluid passes over this body experiences certain drag force. That drag force is actually given to you by F drag is equal to half CD rho AP U infinity square. Now here, normally how do you calculate this CD? That's the most important thing. Okay, calculation of this CD is unfortunately not very easy, but right now what we have is, because of a lot of experimentation results, we have something called CD tables. Okay, so we have, normally the main intention is to calculate this. To calculate this, you should know this. Mathematically it's very, not very much easy to identify what is the values of this CD, but I'll just give you one expression in calculating the this Stokes law of viscosity. But right now you can see half into CD into O AP into U infinity square. This CD is actually identified by shape of this body, the geometry of this body, and also the dimensions of this body actually. Okay, like for example, I'll show you the drag tables which you can see. Drag tables. So you can see, if you go for a lot of imaging, drag coefficient tables. Fine, this is better, I guess. Okay, now you can see, for example, if you open this document, for example from ResearchGate, you can see, I hope you can see here. So depending upon the type of the body, means the shape, and also this reference area, your coefficient of drag values are listed. Okay, now what you'll do if you want to something for your calculation, like for example, you can approximate this, for example, let us say a ball is moving. Okay, then it's a spherical shape. So also this spherical shape, for this particular regimes of Reynolds number of the flow, you can see there are certain drag coefficients which are acting here. Okay, so like this, in actual case, based on the experimentation results, these tables were generated, and you will pick the value of CD from the tables actually. Okay, and also this density of the fluid, which this is density of the fluid actually, which AP. What is this AP? AP is for the projected area of solid, onto the plane perpendicular to direction of flow. Actually this equation is in vector form, but I'm not writing because force is a vector actually. So but right now I'm not writing any vector forms and all. I want to make the math simple. Okay, so perpendicular to projected area of solid onto the plane perpendicular to the flow direction. Okay, so perpendicular to the flow direction, and this u infinity is nothing but the free stream velocity. Free stream velocity. Okay, free stream velocity. Like I'll explain you with the help of one example. Actually, if you generally see, for example, a sphere. Okay, so let's say a sphere. You have a sphere. You have a sphere. Okay, now when you have this sphere in general, look what we can talk about this. Okay, so if you have this sphere, then let's say fluid is actually coming in this direction, u infinity. If this fluid is having a viscosity v, and if this sphere is having a diameter d, for example, then you know the drag force acting is equal to 3 pi mu d infinity. Have you seen this anywhere? Drag force acting on a sphere. Have you seen that expression? You might have seen in your +1, or maybe in diploma when you are studying your fluid mechanics, you might have seen this. This is your expression for drag of a sphere, right? Yes or no? Have you seen this? Drag force acting on a sphere in general in laminar flow regime. Yes. Now I'll just try to show you using the previous expression. I'll try to explain you how these terms actually come. Okay, now if you see, this is first sphere, and this is called with one famous name, which is called Stokes' law for drag forces. Okay, why actually Stokes is the person beyond this viscosity also I'll just tell you within some moment. I'll define you what is called Stokes experiment so that you can understand clearly. Again, I'm going in very cut short, okay, because of time constraints. Sorry, Stokes' law. Yeah, this is basically the Stokes' law. Then let us see how you can get that expression. So first of all, FD actually. FD is equal to, Stokes is again the person who conducted a lot of experimentations on viscosity and the effects of viscosity, and drag is one of the effect of this viscosity. So if you see, you have this expression half CD rho AP, density of the fluid, of course, AP into u infinity square actually. Okay, so this is the expression. Now how come these two are equal? You should try to understand certain things. Okay, now for sphere, the CD values for sphere within the laminar regime is given by 24 by Reynolds number, which is from experimentation again. So you can see, for example, yeah, I have shown you these tables, right? Good, let us go to the table once. So if you see, for a spherical body, I hope you can see something here. Yeah, this is actually a sphere. Now when you try to see sphere, for a sphere of diameter d, within the laminar, within Reynolds number for keeping flow, okay, if the flow is very small in general, this is not coming here. You can see the coefficient of drag is 24 by Reynolds number here. Okay, so that's how, if you pick this 24 by Reynolds number, that's we can pick for CD as 24 by Reynolds number. Again, the case here is this flow is actually moving very slow. You can see Reynolds number is less than 1. Okay, so this is keeping flows normally. So 24 by Reynolds number. If you use 24 by Reynolds number here, 24 by Reynolds number. Reynolds number for a sphere, you know, rho u infinity into d by mu actually. Okay, because this should be either the flow direction or actually this is the relative velocity if you write it in vector forms. But right now, if you see, this is u infinity, means let us suppose if you fix the ball and the fluid is moving at u infinity, then what's happening? Or if the fluid is stagnant and the ball is coming at u infinity, anything is fine, into this density of the fluid into projected area. Now tell me, if you project this onto a plane perpendicular, see, this is the flow direction. So for the flow direction, if you take a plane perpendicular, so let us take a plane perpendicular, and if you project this sphere onto this plane, what is the geometry you will get? Please tell me, what is the geometry you will get if you project a sphere onto a plane which is perpendicular to the flow direction? What is the geometry that you will get? It's a what is the geometry you will get? Circle, right? So therefore this projected area is nothing but pi by 4 d square into u infinity square actually. Okay, so this is the expression that you finally have for calculating the drag forces. Okay, now if you slightly simplify this, let us see what you can get. This cancel this 12 times, this 4 cancel this 3 times actually. Okay, and then after this density of the fluid and density of the fluid goes out. This d cancel this d once, this u infinity cancel this u infinity once. So this value is 3. This mu is in the denominator of denominator, you can throw it out. 3 mu pi d u infinity, and this expression both are same actually. Okay, so this is how the drag force formulas is what you will get directly, but the actual cases, this formula you might have, it look very simple, but actually in this formula, since it looks very simple, you may ask me, why cannot you derive the expression of the friction, I mean the drag forces for every body? Because it looks very simple, but actually calculation of this is very difficult. The reason is how to identify this CD is 24 by Reynolds number. That's the main question. Okay, so how do you know this? This is basically from the experimentations and experimental results. You can fix this constants, and these tabulated results, all the tabulated results what I'm showing you, this 0.59 whatever you see in this case, all these are based on the research experimentations, and that gives you the values. Okay, so this is how we actually calculate the drag forces. In many times in GATE examination and all questions, they ask you is, they'll give you the CD value, because undoubtedly you cannot calculate this. So CD is given, and then they'll give you density of the fluid, geometry of the solid, they'll tell you some rectangular plate, some cube, or some sphere, all these things they'll give you. You can calculate projected area for whatever the fluid they give you, and you can also calculate u infinity square actually. Clear? So is this clear to all of you? How to calculate the drag forces? Yes or no? Please type in the chat box. Okay. Normally drag and lift, if you go into a bit of detailed analysis, I think I have a document. Let me show you if I have, because this is the same smartboard in which I taught fluid mechanics. Just we'll see our luck if things go fine. Just some bit of understanding we'll try to have here. External viscous flows. This is external viscous flows, right? Last document. Yeah, here. So I'll try to show you if I could show you. This is external viscous flows. I have talked about yeah, here. This is okay. This is problem solving. Fine. I think in potential flows we had this discussion. Potential flows. Here, I guess. Let's see if we had some discussion about flow past rotating cylinders and all. Okay, so this is the potential flow actually, which I was talking the other day. Guys, yesterday I was telling you, see, whenever you take a geometry like sphere, yeah, anyhow we have taken, for example, past like a cylinder like this, you can see in this case the velocity here and here will not be same. This is the derivation for that, because you can see u theta is minus 2u sin theta, and u radial will be depending on something different actually. Okay, so when you try to calculate this u radial, this is u radial and this is u theta, when you simplify, this velocity profile will depend on this small r. Okay, and as you change the direction between this point and this point or this point, you can see at different radius this has different velocities. That's why the velocity du infinity by dx cannot be taken 0 for cylinder or sphere, things like that. Okay, now let us calculate the lift forces. How we'll actually calculate the lift force is I think I have done here, maybe theta also increases. Now I think in the next part I have done, yeah, maybe here you can see to some extent lift forces. Yeah, vertical acting on the cylinder. So this is the integration of what you have to do. Normally if you take any surface, okay, so in this surface you can resolve this. Normally pressure will be acting normal, so if you resolve this, one component will be acting in this direction, which is actually the drag. Here I did not calculate that because I was not interested in drag forces here, only the generation of lift is what I was interested at that point. So I have taken this direction. Normally if you have the another direction of the fluid, then definitely drag force will be acting in the other half. Okay, so you'll have cos theta, and if you start integrating it, you will finally, after a bit of integration, you will end up with expression. This is for the case of a circulating cylinder, but similarly if you do the analysis for what do you say, if you do the similar analysis for drag force, you can get the expressions for drag. Okay, so I'll try to show you that as well in this dimensional analysis. Basic thermodynamics. Okay, at that time parallel 2 batches was going, I think. So dimensional analysis, maybe here I guess. Dimensional analysis, no, this is 2, maybe 3 somewhere here. No, this is dimensional analysis, no, external flows, sorry, external viscous flows. Yeah, 4, I think it should be here. Blazer solution, flow separation, we were talking all these points at that time. No, okay, fine. I think I don't have the document right now, but somehow I'll try to post it in the Telegram. Okay, but can you all understand that if you see in actual case what happens? If you take this is the surface, for example, on this surface when pressure acts like this, you can actually resolve the pressure into two parts. Okay, so one corresponds to drag and one corresponds to the lift force, and you will have to take a normal vector at this point and you have to do certain analysis. Okay, so after doing this analysis, this is the formula what you get. Clear? So can you just read those formula ones? Can you read those formula ones? Which this one, half CD rho of the fluid projected area into U infinity square actually. Okay, so this is the expression for the calculation of drag force. Okay, so is this clear to all of you till this point? So please type in the chat box. Preet, do you have any doubt here in this formula? So please type in the chat box. Okay, everything is fine till this point. Okay, so anyway, for lift the same thing. Here you'll have CL. In case for lift, same things gets valid. Only the sin theta component will change in the integration. So half CL is what you have. OF projected area, again U infinity square. This CL calculation is again depending from tables. Okay, so a lot of mathematical and integrations and all you have to do to get this CL. So CL and CD, if you can identify, you can calculate drag and lift forces. Okay, this calculation of drag looks very easy when you take this formula, but actually in this formulas identifying the CD and CL is a little hectic job. Fine. Anyway, one thing that I just want to go before we go to dimensional analysis, I just want to tell you something about Stokes experiment. Stokes experiment, okay, which is a bit interesting to know actually. Normally if you see this value, kinematic viscosity, you know kinematic viscosity is highly powerful actually at many points. So if you have this kinematic viscosity, for example, this kinematic viscosity has SI units. Normally the value of nu is very small. Okay, so this value is very small in general. You can see values are like of the range 10 power minus 2, 10 power minus 4 meter square per second and all. So if you want to express them in CGS units, what is the CGS unit of kinematic viscosity? I have told you in the first lecture. So please tell me, what is the CGS unit of expression will remain same. Okay, meter square per second is the SI units. Okay, I'm talking about CGS. Yeah, for CL and CD they can have equation in terms of Reynolds number is what they'll provide. Okay, so in such cases you will calculate Reynolds number and you will calculate CD. Stokes, right? So here we have Stokes CGS unit. CGS unit. Okay, now what is the relation between this? Basically why this is given as Stokes, that comes out from the Stokes experiment. Look, what is the Stokes experiment is actually, you take a viscous oil in general, see here. Okay, so you have a fluid, some fluid which you don't know generally. Let us say density of this fluid is known. Density you can calculate very easily. Just put this fluid on a weighing machine, then definitely you know mass, and also you know the volume occupied by the fluid. You can easily calculate. It's not stroke, it's Stoke. Fine. Yeah. Okay. So see here, this is actually a fluid, and for this fluid you know density. Okay, you know what is density of the fluid. Fine, because density can be easily measured. You just measure the mass. You also know what is the volume occupied by the fluid. You have a lot of containers, so you know what is the volume, so you can calculate density easily. But let us suppose you don't know what is the dynamic viscosity, kinematic viscosity of this fluid. Okay, because kinematic viscosity plays an important role. Then what Stokes has done to identify the kinematic viscosity of this fluid is actually, he has let a small ball. Okay, so a small heavy steel ball, small heavy ball actually. Okay, so this is a small heavy ball in general, density of solid, for example. Now if you leave this ball here, what happens eventually? We have seen one case, whenever any body starts feel it dropping in viscous fluid, after some particular time the velocity of the body becomes stagnant. You have seen in the first class I have shown you one expression like this. Whenever you have a fluid layer like this means whenever you have a viscous effects acting on the body, the gravity will try to accelerate this body, but this viscous forces will try to slow down this body, and there comes a compromise. After some time, if you see velocity versus time graph, this is V terminal. So this velocity will increase and finally will become asymptotic to Vt. We have seen this in the first case, in the first chapter. Do you remember this? Whenever gravity and viscous both are there, then this will try to stagnate, or basically it will try to steady the flow, such that the body after some time will try to move with certain steady state velocity, which is called terminal velocity actually. Right? We have seen this in the first lecture. Now, if this is the case, same thing actually applies even here. And what happens after some time, this body starts moving with terminal velocity. Okay, so this body starts moving in the fluid with the terminal velocity. Now, Vt. Now, what Stokes has done, this chamber he has made transparent. This is a transparent chamber, like a glass or something. Transparent. So, what he has done, he has identified two marks. This is L, and with the help of a stopwatch, or generally with the help of a timer, simple clocks even those days, what he has done, he has calculated what is this L by T. Okay, means the distance traveled by this ball is L, and the ball has traveled this distance in a time T. So this L by T gives something. What is that? Let us suppose if this ball is coming down with a velocity Vt, this L by S is actually equal to something. What is it? L by S is actually equal to something. What is it? V, correct? This Vt. Yes, this Vt is nothing but this. So this is actually your Vt. Now, if this is Vt velocity, which is actually this terminal velocity, which is the moving velocity of the block actually. Now, if that is Vt, look, the ball moves at terminal velocity Vt, which is actually a constant velocity. Terminal velocity Vt. Okay. Now, if this is Vt, then try to understand what is the sigma f acting in the y direction on the ball. This should be 0. And what are the different things acting on this ball actually? If you go for the free body diagram of this ball, you can see on this ball there is weight of the ball which is pulling it down, and then you have two forces actually, buoyancy and also viscous effects, which is nothing but the drag force. Okay, because we have taken viscosity also now. So this is weight, this is buoyancy force, and this is drag force actually. Okay, now if you apply the force balance, definitely this W has to be equal to buoyancy plus drag force in general. So let us say if you write certain expressions for this, weight, density of the solid into volume pi d cube by 6 into G is equal to buoyancy force, density of the fluid pi d cube by 6 into G, because complete ball is getting submerged, plus viscous force. So let us suppose if this is a it's a ball actually, so spherical in shape. So drag force is nothing but 3 pi mu d v actually. Okay, so velocity at which it is traveling, which is terminal velocity. So this is how we can actually apply the force balance. Now if you can apply the force balance in this way, what you can do here is this pi d can be cancelled in every term. Then after you can see yeah, I think this is what you can do. Now your main intention is to calculate this viscosity. Okay, so generally rather than knowing the densities of the bodies, it's better to know the specific gravity of the body, correct? So if you want to calculate the specific gravity, for example, let's say if you define this as specific, if you divide this with density of fluid, for example, in all the yes, you can divide this with density of this fluid. For example, if you divide with density of the fluid actually, then let's see what you have, density of the fluid, and here also density of the fluid actually. Okay, then if you shift this term to the left hand side, we have d square g d square by 6 times of rho s by density of the fluid minus 1 actually here. Okay, so this term if you shift it this side, we have g d square into by 6 is also here, density of the solid by density of the fluid minus 1 is equal to, now 3, you can shift this 3 here, you will get 18. Okay, so you'll get 18 here because this 3 can come here and it's 18 by Vt. Vt is also known to you, so 18 times Vt. Okay, so Vt is also here, so Vt is here. So this is equal to mu of the fluid by density of that fluid, which is nothing but kinematic viscosity of the fluid actually. Okay, so this is actually the expression for kinematic viscosity of the fluid, and in this expression you actually know what is G. G is known to you, you can 9.81. So rho by G, weights, didn't get you. It's correct, right? Okay, it's means density is what you're talking, right? So this is what you have. Now in this you can measure what you know what is G, you know what is diameter, because if you are given a diameter, then you can actually measure the if you are given a ball using vernier calipers or some other techniques, you can measure the diameter. This quantity is known to you because you can easily identify densities of the solid and also fluid. Then Vt, you know, because you have a physical time scale to calculate, you have a length and a time, so that you can identify what is Vt easily. So this all quantities are known, which means this formula can actually give you an unknown, which is a very powerful unknown, which is nothing but kinematic viscosity of the fluid. Understood? So that's how this kinematic viscosity of the fluid is calculated from all the parameters which are known to you. Clear? So this is Stokes' experiment, and Stokes is the person who actually worked out this experiment and gave an expression to calculate kinematic viscosity in this case. Okay, so that's what you have. Clear? And now all these terms are interconnected. Like for example, if you change the solid or if you change the diameter, this Vt will change accordingly, such that this, it's one important thing about this is, as long as you don't change this fluid, this will never change. You can change diameter, you can change density of the solid. Like for example, you can use some different solid. Depending on these two, this Vt gets adjusted accordingly, such that this total term will remain constant as long as you don't change the fluid. Okay, so this is one very powerful experiment actually, and this gives you the kinematic viscosity of the fluid, and that's why this is given. Clear to all of you? Okay, so this is one technique for calculating kinematic viscosity. Very simple technique. Okay, normally nowadays you have viscometers, all these things, but you know, at those days, without doing much, simple experimentation could actually give you this expression. Okay, clear? Now let's go to, is that clear to all of you? Did you all understand how to calculate the drag forces if CD is given to you? Sometimes what they do, normally you will see later, CD is actually a function of Reynolds number. Okay, so like here I have taken 24 by Reynolds number, like that in general CD for any flow will be some function of Reynolds number, and they'll give you some they'll give you certain important expressions for calculating CD. Like for example, they may give you 0.2 plus 48 by Reynolds number, some expressions like this. So whenever they give you things like this, then just calculate Reynolds number in the flow, substitute here, calculate CD. Okay, like how you calculate heat transfer coefficients and all. Clear? Why viscosity is important? Because every fluid has viscosity and it will try to show its effect on bodies, plates, whatever. Okay, if you are moving, as long as you are moving inside a fluid, definitely you are under the effect of viscosity. Okay, there is a boundary layer acting on you. That's why. Now let's move quickly on to this dimensional analysis for now. Okay, so dimensional analysis here. This is again one of the most powerful chapters, not only in mechanical, for any discipline like electrical, civil, chemical, whatever you take. This is like the most fundamental and important chapter actually. Like yesterday, you have seen the advantage of doing scaling analysis. Okay, by doing scaling analysis, you understood out of a big equation which terms of what scales actually. Okay, like for example, you have neglected compared to pressure, inertia terms are less in case of y direction, so you have neglected them. So like this, scaling analysis makes you understand the things very easily. Similarly, this dimensional analysis is more powerful because this dimensional analysis makes you understand when you are doing any experimentation or when you are doing any trying to solve any physical problem, what are the governing forces in that particular equation is identified by this dimensional analysis. And also there is one particular principle first to start with, principle of dimensional homogeneity, which you might have seen actually. Okay, our complete dimensional analysis is based on this principle. So principle of dimensional homogeneity. Principle of dimensional homogeneity. Have you ever seen this principle? Any one of you? So please type in the chat box. Have you ever seen this principle of dimensional homogeneity? Seen? Seen, right? Yeah, basically this is nothing but if you have an expression, like for example, if I say dimensions on both sides of any equation, both sides of any equation must be same. If this is not happening, normally this don't happen in case of some empirical relations and all, so definitely we can have certain error. different unit can multiply or divide. Yes, like LHS is equal to RHS. Similar unit can be added or subtracted. Yes, correct. Okay, so you can see normally if you take any equation or if you take different terms in an equation, if you are doing addition, okay, or subtraction, then definitely the terms or the dimensions of both the terms should be same actually. Okay, like for example, you can add only force with a force. You cannot do force plus torque. Okay, you cannot do this. You can do this actually. Clear? So that's what we practically mean by this. Okay, now anyway, to do this, we need to have certain understanding on fundamental dimensions. Fundamental dimensions. So what are these fundamental dimensions? Do anyone know what are the total number of fundamental dimensions? Total number of fundamental dimensions. What are the total number of fundamental dimensions? 7, right? Yeah, totally we have 7. All of you? Only 1 or 2 know? 7 fundamental dimensions, right? So what are the 7 fundamentals actually? Mass, length, time, current, temperature, luminous intensity, and mole generally. Okay, so these are 7 fundamental dimensions. Okay, and the units of this is actually candela, CD. Don't get confused with this CD. CD is actually coefficient of drag here, but this is CD again. Candela is the unit of luminous intensity. Like mass, you have kg, length is meter, time is second, current is ampere, Kelvin is for normally temperature. Okay, luminous intensity candela, and mole, you have mole actually. These are the 7 fundamental dimensions. So these are also called fundamental physical quantities. Any quantity that you derive using these 7 quantities is called a derived quantity in general. Okay, so like for example, you see force. Force is not a fundamental quantity. You cannot find force in this, but you know force can be written as mass into acceleration. Acceleration can be written as velocity by time. So now velocity can be again written as length by time. So now you can see this quantity is derived by some combination of these 3 fundamental quantities: mass, length, and time. Clear? So that's how you can actually calculate. Now what is luminous intensity? The effect of lighting. Okay, so maybe you can find it in any textbooks of optics or even light. Okay, you can go there. So this is luminous intensity. Clear? Now the main advantage why we use this dimensions is actually, let us suppose if you are doing some experimentations, you know you have to conduct a lot of experiments as engineers. When you are conducting some experiments, okay, this dimensional analysis helps you. What are the rules or what are the set of guidelines you have to follow when you're doing experimentation? Like for example, let us say I am testing some airplane. I want to do some simulation test of an airplane. Okay, so let us say there is an airplane here. Okay, for example, there is an airplane like this. If this airplane is actually flying in this direction, in actual case, now if we want to test in lab, then clearly one thing is very important: you cannot test a big airplane inside a lab. Okay, you will try to make a small model of it. Okay, so here there are 2 important things which I want to mention: model and also prototype, or prototype first and also model. Prototype is actual entity in the field, actual entity in field. So here this airplane is actually the prototype. Now model is something what you design for lab, designed for lab testing, designed for lab testing. Okay, now can anyone tell me out of these 2 which is big in size? Can anyone tell me out of these 2 which is larger in size? All this stuff should do by us or software. Normally you have a lot of softwares nowadays. Everything you can do in general. Okay, all of you, everyone, please type in the chat box. I think I'm getting comments only from few guys. All right, just a minute, let me refresh my chat button once, because the video got stuck somewhere. I was not able to see all the comments. Just a minute. Where is this chart? Yeah, fine. Now out of these 2 which is large? Actually prototype, right? Actually you can see you cannot decide which is large out of these 2. Okay, sometimes prototype can be of bigger size, sometimes model can be of bigger size than the prototype. Okay, I'll explain you 2 examples. Model can be of bigger size compared to prototype. Actually, this can happen compared to prototype. Like when I explain it this case, you may feel depending on the situation. Yes, exactly. It depends on the situation what you are experimenting. Look, if I test for example an aeroplane, then definitely the actual aeroplane will be of larger size and the model what you make in the lab will be of small size. Okay, but let us suppose I am studying heat example. If I am studying heat transfer of microelectronics, or let us say for example simple electronics, or let us say thermal management of laptops, for example. Okay, so thermal management of laptop. So in your laptop you see you have a lot of chips and all electronic sensors, everything. So whenever you see these things, they generate a lot of heat when they operate. So let us suppose you are designing some heat or fluid flow, for example, means the heat transfer you are designing. Then compared to the laptop small chips and sizes, microprocessors and buses, all these things, you will actually simulate a larger versions of them and then you will do the analysis. Correct? It's very difficult for you to operate. Similarly, if you're working on fluidic microchannels, it will be very difficult for you to analyze point to point situation at that scale. Okay, so what you do, you will generally scale up the things, you'll create a models which are of larger size, and then you do certain experimentation. Clear? So that's how sometimes model can be of larger size as compared to prototype. Okay, so never fix in mind that prototype is of larger size always. No, need not be. Clear? So anyway, these are the things. Now when you are designing your model, for example, okay, let us suppose you want to do some experimentation. So for that you have to create a model. Now when you are creating this model, definitely there should be certain similarity between the model and also the prototype. Yes or no? It's not like if I want to test an airplane, for example, on the if I want to test the functioning of an airplane, it doesn't work if I test some capillarity rise or capillarity fall in some tube. Okay, so there should be certain model similarity. There should be certain similarity between model and the prototype. Now what are the similarities for developing models? Similarities for developing models, actually. If you want to design certain model, what should be the similarities that you should follow? The first thing is geometric similarity. Geometric similarity. Like for example, let us suppose if I am testing a cube. Okay, so effect of fluid on a cube, for example. Okay, or so let us say a rectangular plate, this is A and this is B. This is prototype. Let's say I'm developing a small scale model. So model is something like you have a small scale, so that you have A dash and also B dash. Now whenever you are doing testing, the first thing that you should follow is the model and prototype should be of majority similar in shape, and the corresponding dimensions. You know what is similar? Okay, similar triangles you might have seen. Similar is nothing but same in shape but maybe different in size. So like that, if you see this A dash by B dash, or this, you can write this fraction in another way. This A dash by A should be same as B dash by B. And similarly, if there are any other dimensions, then first of all you should make the model and prototype of same shape and they should be similar. Okay, similar, right? Similar triangles, for example, if you see, they should be same in shape but they can be different in size, actually. So this is called geometric similarity. Then you talk about the second thing, which is kinematic similarity. Kinematic similarity. So what is this kinematic similarity, actually? So see here, let us say if you are developing some fluid flow, for example, and the particles in the actual prototype are expected to have certain variation, which is like V radial ER cap plus V theta E theta cap, for example, and VZ EZ cap. Now between prototype and model, VR of model by VR of prototype should be identical to V theta of the model by V theta of the prototype should be identical to Vz of the model by Vz of the prototype, actually. And practically attaining this is very difficult. Okay, it's not very easy. For few minutes, literally forget which subject I'm learning. Yes. Okay, so let's see here. So this is VP, V theta m, V theta p, and VZM, and also VZP. So this is the kinematic similarity. But practically maintaining this kinematic similarity is not very easy. Okay, it's not even too difficult, but again, it's not very easy to maintain this kinematic similarity in the development of the models. Okay, then the last and foremost important thing, your prototype and model should have dynamic similarity. Dynamic similarity. So what is that dynamic similarity? Now if you take any problem, for example, let us say if you take for example a aeroplane again for example, okay, or let us say so for example some small body is moving inside a fluid, you take submarine, okay, so submarine is moving inside a fluid. Then in that cases what happens, there are certain types of forces which actually governs the physics there. Like for example, whenever a submarine is flowing in water, inertia force of the submarine, which is basically due to the acceleration provided by thrust and all, and also the viscous forces which are acting on the submarine. So like this, there are certain forces which are acting or which are dominant in that particular physics. So that ratio, inertia force acting on the model by inertia force acting on the prototype, this should be same as maybe viscous force acting on the model by viscous force acting on the prototype. This should be same as because these are different forces which can act on a gravitational force, pressure force acting on the model by pressure force acting on the prototype. Similarly, if there are certain elastic forces, model elastic forces acting on the prototype. Similarly, if you have certain maybe surface tension forces, F sigma on the model, F sigma on the prototype, all should be identical actually. Okay, so this ratio should be same because corresponding forces which are acting should be same. And I am telling you, it is not even very tough, it's almost nearly impossible to maintain all these things equal. Okay, so what we do is, in general, out of all these forces, we identify what are the dominating forces that's governing the flow actually. Like for example, if you say submarine, the case of a submarine moving inside a fluid, submarine, okay, so this is submarine and this is actually fluid. Now if this is submarine and this is fluid, then is it necessary that prototype is big, then whatever dimension big will be, sorry, didn't get your question. It is necessary that prototype is big, then it is necessary, okay, then whatever dimension it big will come in numerator. No, you can keep numerator or denominator, but you should make sure these dimensions are equal. Okay, that's it, this ratio is same. Clear? Can you understand? It doesn't matter whatever this ratio, but this ratio has to be same for all the dimensions. That's what you have to maintain. Clear? It depends on your lab comfort and also the testing apparatus, capacity. Okay, then let's see in these forces. Now let us suppose for example, if you take this case, in this case clearly elastic forces means the compressibility effects of the fluid will not play much importance, because you can understand the submarines generally they move with low speeds, okay, compared to airplanes and all. So when they are moving with low speeds, it's not possible that this water will experience certain compressibility effect. So out of these equations, for simulating this condition, it's not very much important to see the similarity of elastic forces and also things like surface tension and all. Correct? So depending on situation, what we do, since it is very difficult to maintain the similarity of all these things, we will pick the set of important or predominant forces and we will make sure that that ratio is important. Like for example, in this case, inertia and viscous forces are very much important. You will try to maintain this part of the equation, and generally other terms are not of much importance. So even though there is certain imbalance here and there, you will try to neglect that and you will try to maintain certain exact things. That's why experimental results will always show certain deviation with actual physics, because we do these things. Understood? When you are developing some models in the labs, clearly you cannot follow all these things to happen. So therefore, because of neglecting the similarity of some terms, there is certain always different errors which comes into the picture. Yes, others can change is fine. Yes, the changing of this is fine because their magnitudes are not very much dominating in this case. Okay, like practically when a submarine is moving, almost there are no compressibility effects, very minute, 0.00 of that order density changes which can be neglected in general. Clear? Okay, now this is what you have, inertia, viscous forces. Now depending on the situations, like for example, if inertia and viscous are predominant, we'll take this part should be equal. Okay, if inertia and the gravity are predominant, we'll take inertia and gravity forces. So we will scale the corresponding terms. Okay, now let's see techniques or methods for doing dimensional analysis. Methods for performing dimensional analysis. The first method, which generally looks to be easy but not very helpful to us, is a Wallis method. So what is this Wallis method? Okay, so let's understand things. For example, let us see delta, boundary layer thickness. Okay, let us take this common example because we have talking about delta since last one day. So if you take this delta, boundary layer thickness, for example, on a flat plate. Okay, so let's say there's a flat plate. There's a flat plate like this, and some fluid is actually moving. Okay, and this is x. This is x actually here. Now this is x and this is y. Then at any given point, for example, at a section x, this thickness is delta. Now scaling actually tells you this delta by L is of the order of magnitude Reynolds number. Dimensional analysis also tells you some similar thing, but in a different way. Look, delta, for example, if I ask you what is the value of delta, one thing, delta will depend on, definitely from your physics understanding, as x increases, delta increases. So this will depend on x clearly. It also depends on how fast the flow is coming, u infinity, this. You also know it depends upon the fluid properties, O, mu, these things. Now, by understanding or looking at this problem, that this delta will depend upon x, at what section you want delta, because you can understand clearly as particles slow down, definitely this x increase will increase delta. So this delta depends upon this x, u infinity, density and u. Now, what Wallis method actually suggests us is the dependence of delta on those terms is power law kind. Like he suggests us, like there is a physical quantity x which is depending on x1, x2, x3 and so on xn. It suggests a model which is of the form x1 power m1, x2 power m2, x3 power m3 and so on xn power mn actually here. Okay, so this is what this model says, means the relationship of the variables, of the independent variables in calculating this x, means this x and these parameters are related in a power law kind variation. You can see there are there are powers actually of this x1, x2, x3 and all. Clear? So this is the solution. Now if you see, for example, definitely delta, therefore delta is actually x power a, u infinity power b, for example, rho power c, mu power d. Okay, so let's say we have this x power a, u infinity power b, rho power c and also mu power d. Now clearly if delta is equal to this expression, then definitely the dimensions should match. Yes or no? Dimensions of x power a, u infinity power b, rho power c and mu power d. Why this should match? Because of principle of dimensional homogeneity. If you have an equation, then definitely both the sides of that equation should match in terms of dimensions. Okay, so let us see what are the dimensions of different quantities that are involved. Now dimensions of delta, delta is a thickness, so L is the dimension. Dimensions of u infinity, velocity, meters per second. This is also same as dimension of x actually here. Dimensions of density, kg per meter cube. Dimensions of dynamic viscosity, kg per meter second, SI units. So this is the expression of dynamic viscosity, correct? Meter, m, L power minus 1, T power minus 1 actually here. And if they can ask how they will form equation, how they'll form question, yes, definitely. Okay, let's go in a systematic way. Definitely at the end I'll try to solve certain questions. Okay, so this is delta, u infinity, rho and mu actually here in this case. Now if you substitute these expressions, what you will get? Dimensions of delta L should be equal to dimensions of x power a. So x is having the dimensions of L again, so L power a into then u infinity power b. U infinity is L t power minus 1, so L t power minus 1 power b, so t power minus b into density power c, so m L power minus 3 power c, so m power c L power minus 3c into dynamic viscosity power d, so power d of these things, m power d, L power minus d, t power minus d actually. Okay, so this is what you have. Now if you have these things, the dimensions of L power 1 should be equal to m power c plus d, L power a plus b minus 3c minus d, t power minus b minus d. Okay, so this is what you get, right? So t power minus b minus d, this is what you have. Now if these two terms has to be equal in terms of dimensions, clearly this c plus d has to be 0, this complete expression has to be 1, and this complete expression has to be 0, correct? Only if this is 0, 1 and 0, the dimensions will match on both sides, otherwise the dimensions will not match. Clear? So let us see. C plus d is equal to 0. This is one equation which implies c is equal to minus d. Okay, then a plus b minus 3c minus d is equal to 0, and also b plus d, because minus b minus d is equal to 0, so you can write b plus d is equal to 0, so b is equal to minus d. Now the problem here is you have only 3 equations in terms of fundamental, similar get together and LHS, then all the equation are done. Yes, correct. Okay, so if you see, if you have this b plus d is equal to 0 and b is equal to minus d, then the problem here is you have only 3 equations but you have got 4 unknowns. Okay, so what you will do, normally when you get these cases, we'll call this as, normally in linear algebra, in matrices, you might have seen, these are called one parameter system solutions. One parameter system of equations actually. So you have 3 equations but 4 unknowns. Okay, so what we'll try to do, we'll try to convert all these things in a single unknown. Since c is equal to minus d, b equal to minus d, let us also try to convert a in terms of d, because all these two are directly in terms of d, it's easier for us. Okay, so in this you can see a is equal to 3c plus d minus b. Okay, so 3c, 3 times of c is minus 3d plus d minus b is minus of minus d, which is plus d, so this is minus d actually. So a is also minus d. Now you can understand this implies delta is equal to here x power a, so x power a is actually minus d into u infinity power b, u infinity power b actually. Okay, so where is u infinity power b actually? B is equal to minus d. Okay, so this is also minus d into then density power c, so density power c, so c is again minus d into, okay, and mu power d, mu power d actually. Then you can understand delta is actually some function of this dimensionless combination mu by rho u infinity x power d actually here. Okay, so this is function of this term. Now clearly you can understand this term is actually dimensionless. Dimensionless actually. Okay, so this is dimensionless, and clearly this number what you got here, this dimensionless combination is nothing but your Reynolds number. Okay, so this is your Reynolds number. So this tells you, if you want to simulate this in lab, the dimensionless number that should be same between your model and prototype is actually this number. Okay, so in this case, this inertia and viscous are predominant. So in case of inertia and viscous forces being predominant, this term, this dimensionless combination has to be made similar between the actual prototype and the model. So this is how, by performing dimensional analysis, you will come to know which dimensionless numbers you have to make equal between the model and the prototype actually. Okay, I'm not telling this is actually, look, sorry, you have a question, right? What is that? C equal to minus d. Okay, a plus b minus 3c minus d is equal to 0. Delta, here something is missing, please check carefully. X power a, u infinity power b, rho power c, mu power d. L power a plus b minus 3c minus d is equal to 0. Okay, so a plus b minus 3c minus d is equal to 0. So a is equal to c equal to minus d, b equal to minus d. This is minus d, this is minus d. So 3c plus d minus b, so minus 3d. So this is minus d actually. So if you do this, look, we are just telling this is not equal exactly. Okay, this is some function of this. Okay, so dimensionally it depends like this, not exactly, because some constant should be there here. So it is just the dimension. Clear? Yeah, it is hereditary, but even though this is dimensionless, then clearly we are just telling this delta depends on this. Okay, this equality that means only dimensional equality, not the exact equality. Dimensional equality. Clear? So means practically we'll make sure that this delta will depend on this dimensionless combination, which is actually the Reynolds number in this case. Okay, so when you are doing the testing, you should make sure this Reynolds number combination should be same between the model and the actual prototype. Okay, is that clear? So basically performing dimensional analysis gives you what parameters or what dimensionless combinations you should keep constant between the model and the prototype. This is how we have. Okay, then this technique may actually seem very easy, but you will feel difficulty with this technique if number of parameters are actually large. Okay, means I'm telling you, let us suppose if you have, for example, here what can you say, like you have 3 equations. Okay, now if these are 3 equations but you have 4 unknowns, okay, but let us suppose you have only 3 equations with 5 unknowns, 6 unknowns and all, then this analysis becomes very complicated. So in such cases what you will do is you will go for this Buckingham-Pi theorem. Buckingham-Pi theorem actually. Okay, so this Buckingham-Pi theorem, again this theorem is same in any subject in fluid or heat transfer, wherever you do, this technique is actually same. Now what is this Buckingham-Pi theorem tells you, or how it actually analyzes the things. Now let us say x depends on x1, x2, x3 and so on xn, for example. Okay, so this is xn, it depends on n terms like this, or n minus 1, let us say, because I just want to tell you one thing, this is xn minus 1 actually. Okay, so let us say there are total n minus 1 quantities and this is depending upon so this is the first time learning this theorem, it's okay, but it's very easy theorem, so see carefully. x1, x2, x3 and so on xn minus 1. So if there are total n minus 1 fundamental dimensions on which this x is depending, what we write? We write this as f of x, x1, x2, x3 and so on xn minus 1 is equal to 0 actually. Okay, like for example, you can see you have x is equal to e power y. Okay, then you can write this equation as x minus e power y is equal to 0. Correct? So this is of the form x comma y is equal to 0, but here you write it as x is equal to some function of y. Okay, so this can be written as some function capital F of x comma y is equal to 0. So this is called explicit form and this is called implicit form in maths. Okay, you can see here you have both variables on the same side, but here the variables got separated actually in this case. So this is in general called the implicit, and sorry, this is explicit and this is implicit actually. So when you write this, you can understand in this function total there are n variables here in this case, n variables, correct? Now let us say these n variables, if you take the dimensions of x1 or capital X, you have some m power something, l power something, t power something. Okay, so a1, b1, c1. x1 you have m power a2, b2, t power c2, and also you can have some other things, Kelvin and all, depending upon the whatever the subject you do, like heat transfer, you have Kelvin also here, Kelvin power c, d1, all these things and so on. If you do for xn minus 1, you have m power an, l power bn, t power cn and so on. Then the main thing is all these quantities are involving, for example in fluid mechanics course, what we do right now is we will take these 3 fundamental dimensions are involving, because the common things what we deal, density, dynamic viscosity, what do you say, density, kinematic viscosity, areas or some other things, all these things involve m, l and t only here. Okay, but in general the theorem is for if these n variables involve m fundamental dimensions, okay, so let's say this involve in m fundamental dimensions, then this equation can be reduced to then total terms or total variables in f can be reduced to n minus m fundamental dimensions, or n minus m, sorry, terms, n minus m dimensionless terms, n minus m dimensionless terms, which are also called pi terms actually. Okay, so they are also called pi terms here. So they are also called pi terms. Okay, so I'll try to explain with the help of an example in identifying this pi terms. Then we will see how we can actually work out this theorem. Okay, so first thing, let us say for example, what example you can take? Let us say drag force. Okay, so drag force, you know, actually the formula is half CD rho A U infinity square, all these things. Okay, then let us understand one thing. For example, you know, let us say you have a sphere. You have a sphere, and let's say some fluid is actually coming in this direction, U infinity. Okay, and this is having some diameter D. Then this fluid is having some density, viscosity. Okay, it's coming at U infinity, all these things. Then let's see, you know, drag force will actually depend on density of the fluid, dynamic viscosity, okay, and velocity, these things. Okay, so let's say, and diameter of the, you know, diameter of this sphere, all these things. Okay, so clearly, you know, drag force depends on these quantities. Okay, now whenever these are the quantities, you can write this as some function of drag force, density of the fluid, dynamic viscosity of the fluid actually here, U infinity D is equal to 0. Okay, now here you have total 5 terms. Okay, so total 5 terms actually. Now if you start writing the dimensions of these 5 terms, you have expression for force. Force is mLt power minus 2. Correct? This is what you have as the dimensions of force, because you can see mass into acceleration. So mass into acceleration, acceleration is velocity by time. So mL by t square. Okay, so mL by t power minus 2 is what you have, mLt power minus 2. Now similarly, if you take this density of the fluid, kg per meter cube, dynamic viscosity kg per meter second, U infinity meters per second, and diameter you have L actually. Now if you see all these quantities, there is involvement of m, L and t. There is no other fundamental dimensions. m L power minus 3. Yeah, density is m L power minus 3 kg per meter cube. Okay, now if this is m L power minus 3, then in all these cases, if you club together, if you club all these quantities together, there are involvement of 3 fundamental dimensions. You have mass, length, and also time. Okay, length, mass, length you have, mass, length, time you have, again length, time. There is no other variable again other than this mass, length and time. So these 5 terms involving 3 fundamental dimensions. 3 fundamental dimensions actually. Okay, so they involve 3 fundamental dimensions, and clearly the 3 fundamental dimensions involved are mass, length and time actually. So therefore this equation can be reduced to number of pi terms is equal to total number of variables. There are 5 variables minus these 5 variables are involving 3 fundamental dimensions. So 5 minus 3, which is 2 actually here. Okay, so that means this complete function of 5 terms can be reduced to a function of 2 terms actually. Okay, so like you can write some function of pi 1 and pi 2 is equal to 0 actually. Okay, so this is what you have, function of pi 1 comma pi 2 is equal to 0. Now this is what I have explained till this point. Is it clear to all of you? Did you understand? Basically this example, what you have observed, you have identified number of pi terms should be 2. So that's what I have explained till this particular point. Is it clear to all of you? Now we will see how to perform dimensional analysis. Okay, is it clear to all of you? So please type in the chat box. Fine. Now let's see if this is the case. From here how to work out. Okay, so let's see that. From this point, how to see? Out of n variables, choose m repeating variables. Choose m repeating variables. Okay, so why they are called repeating? Because the model, let them be, for example, let x1, x2, 𝑥3 and so on xm be repeating variables. So in Buckingham-Pi theorem, how the model is constructed? The model is constructed again based on power law model, but slight variation is here. xm plus 1 is given by x1 power a1, x2 power a2 or b1, x3 power c1 and so on xm power m1 actually. Okay, so a b c for example if you do, so m1 let us say, so 1 2 3 and also on, let us say you have certain m variables. This value xm plus 1 is given as pi 1, you can say this. Basically if you shift it, pi 1, the first dimensionless term can be written as x m plus 1. This is what you have. Okay, similarly pi 2, x1 power a2, x2 power b2, xc x3 power c2 and so on xm power m2 into xm plus 2, and finally you can see this pi n minus mth term will be like x1 power a n minus m, x2 power b n minus m and so on xm power b power m n minus m into xn actually is what you have. Look, I'll explain you these things with the help of a simple example, but first of all before that the most important thing is what are these m repeating variables and how to choose them. Okay, you can see total you have n variables here. Okay, so like here you can see total there are n variables because these are n minus 1 and also this capital X is here, so total you have n variables here. Now out of these n variables I have picked m repeating variables, and these m variables what I have picked here I am repeating in each pi term, correct? I am repeating them in every pi term. I am repeating these m variables x1 to xm in every pi term. Now how to choose these repeating variables? For example, if you go to this expression, okay, now clearly you got 3 fundamental dimensions, so out of these 5 variables you have to pick 3 variables. Now how to pick these 3 variables? Let us see. Example of drag force. Now you came to know function of drag force, density, viscosity, u infinity, diameter is equal to 0. You have 5 variables and you came to know these 5 variables are involving 3 fundamental dimensions, so you should pick 3 repeating variables. Okay, so number of fundamental dimensions involved. Number of fundamental dimensions involved is equal to 3. Therefore, number of repeating variables to be chosen. Repeating variables to be chosen should also be 3 in this case. Okay, so number of repeating variables to be chosen should also be 3. Now, how to pick these repeating variables? That's the most important job of this complete Buckingham-Pi theorem. How to actually pick the repeating variables? That's the important thing. Okay, density and dia, because small and easy to handle. Based on easiness to handle, we have to understand certain things when you are picking the variables actually. Okay, see what are the things we have to take care. First thing, rules for picking repeating variables. Rules for picking repeating variables. Point number 1. The variables picked should collectively involve all the fundamental dimensions. Should involve all the fundamental dimensions. 2. One of the variables should define flow geometry. Okay, like for example, if flow is happening, what is the geometry or which particular scale is defining the flow? That's one thing very important. Third, one of the variable should define one of the variable should define, or should, what did I use here? Should define, yeah, should define kinematic parameter. Kinematic parameter. Like for example here, geometric parameter is like, see, geometry, flow geometry is defined by maybe length, diameter, okay, or radius. Anything, radius is anyhow involved in diameter, or width of the plate, something you have to take, okay, so something for the flow geometry. And kinetic parameters, maybe like velocity, acceleration, pressure, which is also a function again of kinematic effect, okay. So like this you can take. Fourth, one of the variable should define property of the system. Like in case of fluid mechanics, we'll see fluid property. Sometimes in terms of heat transfer and all, I think Sandeep sir might have taken you. This can even be material properties like thermal conductivity, all these things, okay. So anyway, so these are the set of guidelines that you should follow when you are picking the repeating variables, okay. So definitely you should pick one variable which talks about the geometry of the problem, okay, like for example in this case diameter. Second, you should pick one variable which actually talks about the kinematic parameters, okay, so kinematic things of the problem like velocity, acceleration, pressure, these kind of things. Third should actually talk about the fluid properties or the medium material properties actually. So that could be density or dynamic viscosity, everything, okay. It's not based on the easiness, but actually it should make sure we'll cover all these things, okay. And when you put all these variables together, you should definitely involve all the fundamental dimensions. The first point is very important. Like now in this 5, if I have to choose 3 properties, let us see what we can choose. So repeating variables, I can talk about. So first, flow geometry, say diameter, okay. So because this diameter is having the dimension of this flow, okay, so basically if this flow is happening, that d defines the time scale. So sorry, didn't get, kinematic means about its motion maybe, right? Yeah, basically kinematic means about the motion of the flow. Now in this case, since this diameter is depending on will actually decide this flow, so I am picking d actually. Similarly, kinetic parameter, you know, this is dynamic, so u infinity, okay, so u infinity is one kinematic parameter that's involved here. Now property of the fluid, density or dynamic viscosity, what shall we take? Density or dynamic viscosity, which you like, anything is fine, we can take anything, but you should take one property clearly. Density will be slightly easy in calculation, correct, because in kinematic viscosity we'll have t also repeating every time. But in case of density, you know, generally if you have to take one between density and kinematic viscosity, we take density because calculation becomes easy. The reason is, see here, one of these repeating variables is kinematic viscosity, for example, then in every equation I'll have some time contribution from the kinematic viscosity, okay, I mean this dynamic viscosity, but actually you can see density don't have time, so equation slightly gets simplified, that's it, okay. So the third variable what I'm picking is density. Now is the choice of repeating variables clear to all of you? Because that's the most important thing when you're doing any dimensional analysis problem. So please type in the chat box, is the picking of these variables clear? What are the different ways you have to follow to pick those variables? It's not like something is easy in calculation, I'm picking it, but you have certain logic behind that, okay. Clear to all of you? Chinmay? Now let us see, therefore these 3 repeating variables you have picked, therefore number of dimensionless terms, yes, size, kinematics and also property, okay. So therefore number of pi terms in this example is 5 minus 3, which is 2, okay. So therefore you can write f of pi 1 pi 2, some function of pi 1 pi 2 is equal to 0. So what is pi 1? So pi 1 is equal to, now start your analysis, d power a 1, u infinity power b1, rho power c1 into, now out of these 5 terms, what are the 5 terms you have? 5 terms are fd, density, dynamic viscosity, u infinity, diameter, okay. So these are the 5 terms. Now out of these 5 terms you have picked 3, then remaining you'll have only 2. So what if repeating will be 4? You have to take the 4th variable, that's it. Let us suppose, for example, see, when I write diameter has the dimensions L, okay, u infinity meters per second, m t power minus 1, sorry, L t power minus 1, then density m L power minus 3. So what should happen is, when you put these together, you have M, you have L, you also have T. Okay, so L is also here. So these three, when you put together, they should involve all the fundamental dimensions which are involved here. Understood? So dimensions of this density U infinity and D should involve all the fundamental dimensions here. Let us suppose, for example, if I am doing some thermal problem, and if I have a thermal conductivity here, then Kelvin, temperature, will also come into the picture. So whenever temperature also is shown, then you have 4 fundamental dimensions. So out of these 6, you pick 4. That's how. Clear? Okay. Then you should pick, since without thermal conductivity you cannot close all the 4 fundamental dimensions involving, then the 4th parameter will be the kinematic, thermal conductivity actually in that case. Okay, because all these 4 variables, when you group their dimensions, they should definitely involve all the fundamental quantities involved here. Got it? Then let us see rho power C1 into, now out of these 5, this is taken, and this is taken. So let us start with drag force. So Fd is what you have. Okay, so this is the variable, so this is the variation. Okay, now if this is the variation, then dimensions of pi 1 should be equal to dimensions of dia L, U infinity dimensions. Okay, so U infinity meters per second, so L power B1 T power minus B1 meters per second, density power C1, mass into this kg per meter cube, so minus 3 C1 into dimensions of Fd. So dimensions of Fd is actually force, M L T power minus 2 actually. Okay, so these are the dimensions. So this, if you slightly simplify, this is dimensionless term, pi term is actually dimensionless. So this is equal to M power C1 plus 1, 1 plus C1, L power A1 plus B1, A1 plus B1 minus 3 C1 plus 1, T power minus B1 minus 2. Okay, so minus B1 minus 2. So this is what you have. Okay, minus B1 minus 2. Now if you see this, this implies, now if dimensions has to match, this 1 plus C1 has to be 0. So C1 is minus 1. This term should also be 0, and this term should also be 0. So this is nothing but B1 plus 2. So B1 is equal to minus 2. Then what is this equation? A1 plus B1 minus 3C1 plus 1 is equal to 0. So this gives you A1 minus 2 minus 3C1. So plus 3 plus 1 is equal to 0. So A1 is equal to minus 2 is what you have. Okay, so A1 is equal to minus 2. Clear? So A1 is minus 2 from this equation, because 3 plus 1 4, 4 minus 2. So A plus 2 is equal to 0. So A1 is equal to minus 2. So if you put this A1, B1, C1 in this equation, you will understand this implies the first dimensionless term is pi 1 is equal to d power A1. So d power minus 2, or let us say Fd is in the numerator, Fd divided by this rho d power A1, d power minus 2. So that can be written as a d square in the denominator. Then after U infinity power B1 actually, so U infinity power minus 2, sorry, U infinity power 2, because you are writing it in the denominator. So into U infinity square into C1 is minus 1. So C1 is minus 1. This gives you rho. Okay, so this is what you have. Fd by rho U infinity square into d square is what you get. So this is the first dimensionless term. Next, pi 2. So pi 2 can be again written as d power A2 U infinity power B2 rho power C2 into, now here you see 3 are repeating variables. Fd is already covered. Then the last thing which is remaining is this mu. So put this mu here. That's it. Okay. So did you understand now what is the meaning of these equations? Okay. So please type in the chat box. Can you understand what is the meaning of these equations now? Okay. Clear? So out of these m repeating variables, then you will start with m plus 1, m plus 2 and all things like that. Okay. Now let us do the dimension analysis for this. M naught L power 0 T power 0 L power A2 L power B2 T power minus B2 meters per second kg per meter cube. Dynamic viscosity of this is T power minus 1. Okay, so this is what you have. So if you slightly adjust this, 1 plus C2 L power A2 plus B2 minus 3c2 minus 1 t power minus b2 minus 1 is what we have. Now clearly if you make this to 0, because this left hand side is dimensionless, this left hand side is dimensionless actually, so b2 is equal to minus 1. This gives you c2 is equal to minus 1, and coming here a2 plus b2 minus 3c2 minus 1 is equal to 0. So this gives you a2 is equal to 1 minus b2. Okay, so minus b2 is plus 1. Let us write straight away. a2 minus 1 minus 3c2, so plus 3 minus 1 is equal to 0. So a2 is equal to minus 1. Correct, because 3 minus 2 is 1. So a2 plus 1 is equal to minus 1. Now clearly you can write this pi 2 is equal to, let us write here, pi 2 is equal to dynamic viscosity by d power a2. So a2 is minus 1, so we have a d here. Then u infinity power b2, b2 is again minus 1, so u infinity here. Rho power c2, c2 is also minus 1, so rho here. So you can see this is the second dimensionless combination which will govern this problem. Okay, so this is the first dimensionless problem, and this is mu is not in the power. Okay, because you can see here when we have done this analysis we did not put a power for mu. Clear? Like here you can see the no powers for the non-repeating variables in this case. Okay, so this is what we have. That means here you identified this can be written as function of pi 1 pi 2 is equal to 0. That means some function of this fd by rho u infinity square d square comma u by rho u infinity d, this is equal to 0, which means you can understand fd is equal to some constant, proportionality constant, into some function of this quantity, maybe some g of mu by rho u infinity d into rho u infinity square d square. Okay, so this is what you can get if you do dimensional analysis. Without knowing the actual formula, you come to know that if you want to calculate drag force, this combination should be same between the model and the prototype, and this is nothing but 1 by Reynolds number. Okay, so which means you have to make sure whenever you are dealing with the case of sphere and the fluid coming in, the Reynolds number between the model and the prototype should actually match. Okay, this analysis is obtained by doing this dimensional analysis, and this quantity, because this is a random function, so between the model and prototype if things should not change, this combination and this combination should be made same between the model and the prototype. And if you compare, this constant k involves half into pi. This pi d square by 4 is nothing but the constant multiplied for the d square to get projected area. Okay, in the actual calculation. Clear? So when you do this dimensional analysis, you will make sure this Reynolds number should be same between the model and the prototype, and also this ratio between the model and the prototype should be same actually. Okay, so using this techniques we'll calculate we'll design the models and calculate the drag forces and all acting on the models actually. Clear to all of you? Is this Buckingham-Pi theorem clearly understood to all of you? How to apply this Buckingham-Pi theorem? Because the Buckingham-Pi theorem method is powerful, because you will never end up with d. You will be able to calculate the powers. Okay, like for example, this 2d, all these things we have calculated, which was not possible in a Wallis model. Okay, so that clear to all of you? Last separation not understand. This one. See, whenever you have some function of these two is equal to 0, I can express this as some function of this. Okay, so for example, f of pi 1 pi 2 is equal to 0, then what I can do, I can write pi 1 is equal to some function of pi 2. Correct? That's what. Okay, simple math, shifting of the equation from explicit to implicit form. That's it, or implicit to explicit. Okay, now so these are Reynolds numbers, fd, rho u infinity square d square, all these things. Yes. Now one thing that I want to talk about before we leave maybe is dimensional numbers. So dimensionless numbers, actually it should be dimensionless numbers. Okay, so dimensionless numbers. So what are these dimensionless numbers? Look, let us see. normally when you're doing any modeling, I told you this set of equations should be valid. Okay, now if you try to scale each of the quantities, let us see inertia forces. So inertia force is like mass into acceleration, correct? Now mass can be written as density into volume, acceleration can be written as velocity by time. So this can be scaled to, okay, so this can be scaled dimensionally to rho L square into, okay, so this V by T, okay, so you can see this L we can write as L by T into V. So this is V again, so this scales to rho L square V square, okay, so this scales to rho L square V square here. Similarly, gravitational force, if you talk about gravitational force, you have mass into gravity. So gravity is constant generally in any term. Basically we are trying to put it in fluid properties, geometry, and also time scale, velocity, kinematic parameters. Understood? Basically what I am doing here is, one is fluid property, one is the length scale, and one is the kinematic parameter. That's what I am trying to fit. Okay, then density into L cube, this is again volume into rho L cube is the density into volume is mass into gravity. Okay, so this is what we have, rho L cube G, this is again acceleration due to gravity, so that's again a kinematic parameter, so I am leaving. Then after, what else, what are the different forces we have taken? F is like here it is, gravity and viscous forces. Okay, so viscous force, let us see the viscous force also. Viscous force, so how will you calculate the viscous force? It's like mu V L, correct? Yes or no? Because you can see scaling in terms of fluid property, kinematic parameter, and also length. So because you can see viscous force can be written as shear stress, mu L square, I think the dimensions are not matching, just a minute. Shear stress into velocity gradient, correct? So shear stress into velocity gradient is what you have, like this. Shear stress is like mu into velocity gradient, so this is mu V by L, this is shear stress into L square. So yeah, mu V L, this is correct. We have mu VL because normally viscous stresses are considered by shear stress into multiplied with area. So shear stress is mu into velocity gradient, so this is the dimension, multiplied with L square, so this is mu VL. Okay, and surface tension force, for example, sigma into L, here there is no kinematic parameter, directly these two themselves will contribute for the complete thing. Similarly, pressure force, elastic forces, actually bulk modulus into L square, this is pressure force. Okay, so pressure force, pressure into area, so P L square. And elastic forces, normally in case of some compressibility effects, bulk modulus into L square, this E is called bulk modulus. Bulk modulus actually, okay, so this is bulk modulus. So these are different scaling of different forces that we have generally in nature. Okay, now let us see, for example, the case of this drag force, for example, whatever you have calculated. In this case we understood this Reynolds number is actually important. Okay, actually yesterday only I started following you and just liked it. Okay, then just follow, that's it. Okay, who am I and what I do, it doesn't matter as long as you understand the things. Okay, so I'll just tell you one thing, maybe if you really want it, like previously before joining PW I was in BRC, and before that I was working with HPCL, and this year I have secured all India rank 10 also in XE. Okay, fine, this intro is enough to believe me and the things what I teach you. So see here, this is Reynolds number. Now if you carefully see, this is ratio of, this same expression can also be identified from the ratio of inertia by viscous forces. Okay, so let's see here. Let us say in a problem where your inertia, example of a sphere, for example, okay, flow of a sphere in a fluid, flow of a sphere in a fluid. Okay, so flow of a sphere in a fluid. Now in this case you can see inertia force of the model by inertia force of the prototype should be same as viscous force of the model by viscous force of the prototype, and the rest of the things I am neglecting them. Okay, so rest of the things what's happening, I'm neglecting these things because these two are the important physics in such cases, which you have seen from the dimensional analysis. Now clearly you can see, if you swap these two, for example, if you shift this to the other side and if you bring this viscous force to the downside, from dynamic similarity of the model by viscous force of the model is equal to inertia force of the prototype by viscous force of the prototype. Now clearly you know inertia by viscous is nothing but Reynolds number of the model should be same as Reynolds number of the prototype actually here. Okay, so this is what you get here. Okay. Definitely. Okay, so anyway, see here, so this is Reynolds number of the model and Reynolds number of the prototype. Okay, now I'll tell you why I'm writing gate again and again. Okay, just give me some time. Okay, just let's show this. So what we are doing, yeah, Reynolds number. So for Reynolds number, if you see the scale of Reynolds number, inertia force, so inertia scales to rho L square V square by viscous force. Viscous force scales to here mu VL actually. Okay, so you can understand this V can cancel this power, L can cancel this power, so this is of scale rho VL by mu. This is what we say as the Reynolds number, because this is obtained by taking the ratio of inertia to the viscous forces. So therefore Reynolds number, whatever you write generally for Reynolds number, this Reynolds number is inertia force divided by viscous force, is you right, and this scales to rho V some length scale which you call hydraulic diameter generally by mu actually here. Understood? Normally it's not like you just write Reynolds number is inertia force by viscous force. Why this inertia force by viscous force is giving this formula is because of this dimensional scaling here. Okay, similarly in some cases, like in the case of free flows, okay, free surface flows, these are submerged flows. Okay, so but for free surface flows where you see like dams or maybe ships, ship also floats. Okay, whenever ship is moving, it gets in contact with the free surface of a water. So in case of these things, you will see, right now we are not doing the detailed analysis, but you will see inertia and gravitational forces are predominant in these cases. Gravitational forces are predominant, and if you take this ratio inertia by gravity, this scales down to rho V square L square divided by gravity. Gravity you can see we have scaled it to rho L cube G. So fluid property, length scale and kinematic parameter. So if you simplify this, density and density gets cancelled, this L square will give this L here. Okay, so this scales to V square by GL, which means V by square root of GL whole square is what you have here. Okay, and this analysis was done by, like how this complete drag and all was done by Reynolds, similarly this was done by a scientist named Froude. So this is called Froude's number, which is basically by inertia by gravity and which scales down to this V by root GL actually here. Okay, it's actually FROUDE. Okay, Froude's. Similarly you can have a lot of things like Euler number, for example. Euler number, basically all these things are nothing but from this master equation. You can see this master equation. Okay, now depending on the type of flow of physics, what happens, like you will make sure certain combination, you cannot, it's not possible for you to increase the complete velocity. So what we are doing is actually we are actually picking some terms out of this. That's it. Do we use this number widely? Yeah, why not? In all the free surface flows we'll use. Basically this significance of this is actually, see here, for example in case of submerged flows, submerged bodies, you came to know after doing certain analysis this Reynolds number is actually important. Okay, so if you want to design any model such that the model actually flow inside the fluid completely submerged, the dimensionless combination that should be same between model and prototype is actually Reynolds number. Similarly in case of any free surface flows, this Froude number, which is basically this combination, is what you should make similar between the model and the prototype. Like V by root GL of model should be same as V by root GL of the prototype actually. Okay, then Euler's number is inertia by pressure forces. Okay, so this scales down to, this actually scales down to inertia rho V square L square by P L square actually. So L square gets cancelled, so this scales down to V square by P by rho actually. So this can be scaled down to V by root P by rho whole square, and this square and this combination is actually called Euler number. Okay, so this is the Euler number. Similarly, you can take whenever surface tensions are predominant, you have different numbers. If I keep on writing, I have to write till 4 or 5 days, but anyway, just I'll try to mention few of them. Inertia by surface tension forces, which now scales down to rho v square L square by surface tension sigma into L. So you can see L and this L gets cancelled. Then this is v square by sigma by rho L. Okay, and this can be scaled down to v by square root of sigma by rho L whole square actually here, and this is your Weber number. Okay, you also have one number which I'll first do the analysis, then I'll ask you what is that number. Okay, so see, if I consider inertia by elastic forces, this scales down to rho v square L square bulk modulus L square. Okay, this gets cancelled, v square by bulk modulus divided by density. Then this is basically elasticity modulus, and this is bulk actually. Okay, so in volume we'll take, so v by root E by rho whole square. So normally in any condition you can see this modulus, which is adiabatic in general, so this quantity square root of E by rho you might have seen somewhere in adiabatic conditions, because right now in fluids we are not dealing any heat effects in this case. So what is this combination? This is nothing but acoustic velocity. So this scales down to v by a whole square, and this actual velocity of the flow divided by acoustic is called Mach number. And normally in all compressible flows this number is very much important, Mach number actually. Okay, clear? So like this you can end up with different numbers. Okay, so Mach, Weber, all these things. Okay, now depending upon the flow physics what's happening, we'll choose which particular forces are predominant, and correspondingly, like for example, if inertia and surface tension are predominant, we'll make sure Weber number is same between the model and prototype. Similarly, if inertia and viscous forces are more, we'll make sure Reynolds number is same between the model and prototype, like I hope we have seen through one example. Okay, fine. And similarly, if inertia and gravity are predominant, you'll make sure Froude number is same between the model and prototype. So things like that. Fine. Is this clear to all of you? Did you all understand different dimensionless numbers? We'll solve one problem maybe, because the time is short actually. So we'll solve one or two problems today, and we will try to wind up the sessions. If compressible flow, because time is up, I'll try to do one thing. Compressible flow lectures I'll upload again on English channel. Okay, so please go there. I means the team actually who is taking care will I'll ask them to upload. So if they upload, then it's fine. Clear? Because anyhow tomorrow we are planning it for turbo machines. Yesterday is the last day, no sir? No, tomorrow is the last day. Okay. Yeah, so to the backend team will just tell to, because in paid batches we have taught this compressible flow in a detail. So I'll try to get them uploaded for you. Okay, so that it would be better. Okay, yeah. So are you all clear with this? Turbo, who will take potential flow link? Yeah, I'll show you these things. Generally, if you see, normally you go to YouTube. Okay, so once you go to YouTube, then you search for 𝐂𝐸 mechanical. Sorry, 𝐂𝐸 English actually here. So 𝐂𝐸, just a minute. English. Okay, so if you go to 𝐂𝐸 English, then you can see in the uploaded videos you have this yeah, you go to videos. Okay, so if you go to videos, you can see control volume analysis also we have uploaded. So potential flows. Okay, so it starts here. This is the first lecture, second, then superpositions 3, 4, 5. That's it, 5 lectures. Hardly it will take you 10 hours of time, but you can understand the complete potential flows in complex numbers. Okay, which is very easy. If you know complex numbers, the power of complex numbers is very, very high. Okay, so just go through these 5 videos for potential flows. Okay, so you go to videos 1, introduction to complex potential function, basic flows, then superposition of basic flows 1, 2, 3. That's it. Okay, we'll try to add one more for compressible flows actually. Okay. Clear? Fine. Now let's solve some problems actually, because it's been quite good time since we solved few problems. So let us solve this problem first of all. For a certain fluid flow problem, it is known that both Froude number and Weber number are important dimensionless parameters. Okay, means you should see Froude number and also Weber number are most important dimensionless parameters. If the problem is to be studied by using a 1:15 scale model, okay, so means for a given prototype, sir, you are talking about gate, acha. Fine, meanwhile try to attempt this, I will say. Generally why I write gate examination every year is, first of all I want to ask you one thing. Are you all understanding the teaching that I'm doing? By the way, someone asked me what is my name. My name is Vinay actually. So are you all understanding the things what I'm teaching you? Like some of you have been there here for so much time. Okay, we have started with fluid and its properties, then kind of, you know, hydrostatics, kinematics, dynamics, control volumes we have seen. Then after, you know, all the thing, Navier-Stokes, external flows, internal flows we have seen, flow through pipes, all this stuff we have seen. So are you all understanding these things? Correct? Okay. Now, and after studying this, definitely you might have understood, you all are understanding it, right? So after studying these things, you will be able to solve the PYQs and all very easily. Okay. Why generally I'm solving less questions is, the main important thing if you go for GATE examination, you should solve all the PYQs of all subjects at least 2 to 3 times, definitely. Okay, PYQs are one very important thing for any competitive examination, and definitely every year almost like 60 to 55 to 60% of the paper will replicate from the PYQs. Okay, not exactly the same questions, but if you solve all the PYQs, you'll have enough knowledge to solve the upcoming questions. Pakka. You can try if you want. Okay, and this year, as per my understanding, if you can get about 60 to 65 marks in GATE examination, definitely your rank is going to be below 150, 100%. Okay, definitely in mechanical. I'm talking in mechanical. In mechanical, if your marks are going to be between 60 to 65, you are going to clearly easily get below 150 this time. Okay, so make sure you are going to get that 60-65 marks at least in the least case, so that you can get very good, you know, locations and postings. So to get this 60-65 marks, PYQ solving is very important. So I hope you have got a PYQ book. Okay, 150, yes, pakka, you can check. Okay, 150 in the least case. If things go beyond, 175 maximum, that's it. Below 200 fix. Okay, so I'm telling you, I hope you got a PYQ book from us. Okay, so that PYQ book, you please go through that. Okay, solve each and every question by a couple of times, actually 2 to 3 times in general. It happens. Now why I write GATE examination is, sir, will you take any PYQ sessions? No, I guess not now at least. Okay, maybe when very close to GATE examination we may plan few, but you know, it again depends on you know, a lot of availability of the faculties and all, because again so many other batches are also going, test series is also going, right? So that's why. Now why I write GATE examination is, when I teach this subject, you know, it's not the first time I'm teaching this. I have been teaching this for past 4 or 5 years. So over the years, what I observed is, when I keep on writing GATE examination, after first 2 years I felt that everything is coming from the notes straight away and all the things. Okay, but let us suppose if that 1 year where things completely happen in a different way, I should check whether my teaching is allowing the students to think for the answers, and whether my teaching is sufficient at least for this subject. Okay, not only me, any faculty will do this in general. It's not any GATE thing about me, anyone will do this. So if you see, like when students are sitting in the exam hall, because of the confidence given by the teacher to the student should feel comfortable in writing the answers. Okay, should feel comfortable in solving the questions. It's not like because of some teaching or because of some skipping of some topics accidentally. Maybe it may not happen intentionally, but accidentally it can happen because of several things like time constraints or some other things. When you teach something, definitely you should not miss any topic which could have enough chance for coming in examination. Any examination, not only GATE, JEE, whatever you take, it should happen. Okay, so to ensure this, I'm writing GATE exam every year. Okay, that's it. Before last year I have got 10, before that I have got 40, 72, I have found a lot of enough below 100. Okay, but the main thing is when I'm teaching, I should not miss anything which could be possible for GATE examination. Because of this, to check the pattern of the questions, and most importantly to check in that examination mindset whether students are able to solve or not. To test these things, I'm applying for GATE every year. Okay, understood? Because after coming out of the examination, looking at paper and saying, oh, this question is easy, that question is easy, this is simple, that is simple, these things are easy. But when you sit in the examination hall, in that environment, are students able to answer those questions or not? This is what I want to test. That's why I'm writing GATE examination. Okay, clear? Got all your answers? Sir, you have done for 𝐂𝐸, we have not solution for 𝐂𝐸. Where can we get that? 𝐂𝐸 is still in a work. Basically I have a document with me in which I have written all the maths solutions. Okay, but I'll see what we can do about it. I'll make sure things gets available for you, at least for 𝐂𝐸 maths, before January comes out. Okay, in the December somewhere. Okay, any more questions? Because anyway, today is the last but one class. Tomorrow we have an extra class actually. So please type in the chat box. Anything more you have to ask? No. Then things are clear. Only 2 subjects completed. Don't worry. Try to finish as much as possible before Pongal time roughly. Then after, for the last 15 days, just keep on revising the things. Some exams will be there almost like every time. You should manage the time actually. So for some exams, hardly you'll be preparing 1-2 days before the exam. It's known fact. It's a universal fact actually. So just prepare for the semester exams, give them in a decent way, and then focus on the GATE examination. Okay, yeah, I understand, because in December majority of the universities will conduct semester exams. November ending and December first 2 weeks exams goes on. So but please be spending some time on GATE every day. Okay, fine. Chalo, let's solve this question before we leave. For a certain fluid flow problem, it is known that both the Froude number and Weber number are important dimensionless parameters. If the problem is to be studied using a 1:15 scale model, what is the meaning of 1:15 scale model? Length scale of the model means if you take any dimension of the model and similar dimension of prototype, this ratio is 1/50. Okay, if the density scale is equal to 1, means what is the meaning of this? Density of the model is same as density of the prototype, because density scale is 1. The required surface tension scale is dash into 10 power minus 3, round off to 10 power minus 3. Okay, so round off to 2 decimal places. Assume that model and prototype are opened in the same gravitational field. Okay, so if they are in the same gravitational field, then let's see. First of all, they told in this fluid flow problem, this Froude number and Weber number are important. So Froude number is V by root GL. Weber, just now we have seen V by root sigma L. Correct? V by root sigma L. Is that what we have? Just check it. V by root sigma by rho L. Okay, so sigma by rho L actually. Rho L is what we have. Okay, so this is the 2 things here. Okay, now if these 2 numbers are important, actually, what is the ratio of these 2? If you define a new dimensionless number, which is the ratio of these 2, or maybe Weber by Froude, anything is same, because if these 2 numbers are important, then this is dimensionless, this is dimensionless, so the ratio of these 2 will also be dimensionless again. Okay, correct? So we will define a new number, maybe we don't know what is that number, so this ratio of these 2 numbers should also be same. So if you simplify this, V by root GL divided by V by square root of sigma by rho L, this is what you have. Clear? Then V is same in both the cases. Then after, you can see this quantity is in the denominator of denominator, so root sigma by rho L into 1 by root GL. Okay, so this is what you have here finally. Clear? So this quantity is dimensionless definitely, because this is a ratio of 2 dimensionless quantities. Therefore, between the model and prototype, the dimensionless number that should be equal is square root of sigma by, this is under square root, this is also under square root, so rho G L square. Okay, so rho G L square is what you have. This is the dimensionless number which should be same between the model and prototype in this combination, in this flow problem. Did you understand what we are doing? Look, they told these two dimensionless numbers are important. So, but we cannot work out with two dimensionless numbers simultaneously. So what we do, we have taken a single dimensionless number, which is ratio of those two. You can even take Weber by Ford, whatever, doesn't matter. So this combination should be same between the model and the prototype, which means you can write this implies sigma by rho GL square of the model should be same as sigma by rho GL square of the prototype actually. Okay, so this gives you, what is the thing they're asking you? The required surface tension scale is dash. So surface tension of the model by surface tension of the prototype. So this is the surface tension scale, like how you have the length scale as length of the model by length of the prototype. Similarly, surface tension scale is this. Now this quantity is nothing but, look, assume prototype and model operate in same gravitational field. Now tell me, if this model and prototype are operating in the same gravitational field, this G and G I can cancel, correct? Because whatever the G is in this model problem, same will be the G in this prototype problem. Okay, is equal to density of the model by density of the prototype into length of the model by length of the prototype whole square actually here. Okay, so this is what you get. Now they have given you one thing, this value is 1, correct? They have mentioned, because you can see the density scale is equal to 1. So if the density scale is equal to 1, density of the model and density of the prototype means, let us say if both are tested in water or something, same fluid, so density is same. So surface tension scale sigma m by sigma p is equal to length of the model by length of the prototype, which is nothing but length scale whole square. Okay, so length scale whole square. So what is this value? Length scale. Length scale is given by 1 by 15. Length of the model by length of prototype is 1 by 15. So 1 by 15 square. So sigma surface tension scale is equal to 1 by 15 whole square. So let us take a calculator and let us pick these values. 1 by 15 square of this. Okay, so 0.004 444 and so on. So this is 4.44 into 10 power minus 3. This is the surface tension scale between the model and the prototype actually here. Okay, so this is what you get, 4.44 into 10 power minus 3. So 2 dimensionals, so 4.44 is what you have. Clear? Even if you do reverse, you will get the same thing, because parameters get shifted. Look, even if this equation is like rho g L square by sigma and rho g L square by sigma, you know, A by B is equal to C by D, C by D is same as B by A is equal to D by C. That's it. Okay, so fractions. Clear? So this is what you have. Did you understand this dimensional analysis in a detailed way actually? Okay, fine. So that's what basically the dimensional analysis is. We have talked about you know, there are some more questions of dimensional analysis, boundary layer, all these things in this. You please try this. Okay, so we have seen this drag forces a bit, then we moved on to dimensional analysis, then we started looking at some dimensionless numbers. Okay, so dimensionless numbers is what we have seen, some inertia, pressure forces, all these terms, different things like how we got. Okay, so compressible flows anyway I was not able to cover today because of the time getting thing. So we should remember these numbers too. You need not actually remember that this is called Ford number, this is called this number and all, but in some sometimes in exams, in 1 mark questions they'll ask you, so better to memorize them. Okay, but more than memorizing them, if you keep on using them, you will get better idea. Like for example, when I'm doing inertia by viscous, that's Reynolds. Okay, you just keep on using them, it will be helpful to you, because in 1 mark questions and all, if they ask you, then you know you'll have something to do. Yeah, why not? These kind of, you can check PYQs. Okay, if you have any doubts with that kind of questions that's being asked, you can check PYQs. In PYQs you have a lot of things. Okay, and also in Abhyas fluid mechanics batches, which we have taken recently, the question practice, you can go through them. Okay, fine. Yeah, 1500 in all these things, you can go there. Fine. So we'll review what we have gone through today in a much broader sense. We have looked at dimensional analysis, and also like you know, we have seen dimensionless numbers, and things like that. Okay, so that's it from my side for today. We'll meet. The class timing of tomorrow is actually 11 a.m. to 1 p.m. Okay, because before that I think Ramanan sir has booked a slot for strength of materials extra class. So anyway, tomorrow the class timing is from 11 a.m. to 1 p.m. Okay, we will see hydraulic machines, turbo machines, and also a bit of turbulence. Okay, so any questions? I hope you have understood everything. If you have any doubts, you can ask me. Any questions or any doubt? Nothing? Okay then, fine. So take care. We'll meet on tomorrow for the last class at 11 a.m. Okay, 1 minute. Yeah, please ask me. So this is known that expression is Reynolds number. Is it necessary all expressions come in that bracket? Expression is dimensionless? Yes, definitely you will get dimensionless quantities. If you want, you can check the dimensions. Like for example, look here in this case, see, you know this is Reynolds number, but if you check this, this will also be dimensionless. You want me to check? I can check for you. See, force m L T power minus 2, density kg per meter cube, u infinity square, meter square, second square, diameter L square. Okay, so you can see this m and m gets cancelled, t power minus 2, t power minus 2 gets cancelled. This is L power 4, this is L power minus 3. So you have a L and this L gets cancelled. Okay, so definitely these quantities are dimensionless because they are calculated by assuming they are dimensionless, and they are dimensionless actually. Okay. Okay. So any other doubts? What do you have? Right. Okay. So thank you all then. We'll meet at 11 a.m. tomorrow for the last class for hydraulic machines. Thank you.